Welcome back from your break. For the next half-hour session, we'll be hearing from Rafal Kolanski, Gerwin, Klein, and Andronick of Proofcraft. They're going to tell us about the seL4 verification roadmap. Yeah, go ahead.
Well, greetings, seL4 enthusiasts. And I'm Rafal Kolanski, but please do call me Raf. I am the co-founder of Proofcraft, along with June and Gerwin, many of whom you already know. Many of you already know them. And I'm here today to discuss the roadmap for seL4 verification, because we have a long-standing history of doing seL4 verification at trustworthy systems over a decade, well over a decade. And we founded Proofcraft to take this vision of seL4 verification and continue it, but in a commercial setting where we're able to be more agile and responsive. Now, the reason we're here, well, one of the reasons we're here, is that seL4 is very special due to its verification. It is unique. But verification can mean many things, and we would like to have a theorem, like a mathematical theorem, where we say, okay, we have verified this and we're done. But seL4 is a real-world operating system which has to be performant and useful for its users. And that means that seL4 itself is evolving. And that means the proofs themselves must also keep evolving. And as Proofcraft, one of the roles we've taken on is to keep this evolution alive. So today, we're going to look at what is the nature of this evolution, some of the challenges that it poses, and what's the plan. And the best source of challenges is, of course, success. And that is something we're quite happy about. When we started this journey around 2005, seL4 was a research group project, and so was the verification. There was just a single platform, a single configuration, and all we had to do was this functional correctness. And that involved going from an abstract specification along with invariant proofs, 2 levels of refinement, down to a formalized C semantics. And this in itself was already a huge success. This was at NICTA and in Australia, and that expanded further due to other interests into having a binary verification, proof down to the binary from the formalized C semantics, and also security proofs, one of which being integrity, which you'll hear about in the next talk, and also system initialization. And this full stack on a single platform, in a single architecture, in a single core, means that we were rather successful, because nothing before that time had this level of coverage, this level of thoroughness, and this level of scale. This was a complete world first. And that attracted a lot of interest, which attracted a lot of customers. Well, some customers. But you've already met, many of you have met customers. And customers are very, very happy creatures. If you have customers, this is great, and they bring joy to your life, because that means your software and your work is going to be used. But they do want to use this work of yours for work of theirs, for their specific applications. And that means they require specialized features. And those features, they would preferably want done by yesterday. And so what typically happens is that our original single platform and single core and single everything proposition now becomes a challenging choice for customers, because now it's, well, do you want the seL4 vanilla flavor, or do you want the mixed criticality scheduling version, which we're going to talk about, and I'll talk about a bit more as well. Do you want a plain, solid RISC-V cone? Do you want a cinnamon-flavored ARM cone, or do you want a plastic cup of x86? And furthermore, do you want to double up your cones? Like, is 32-bit thickness is good enough for you? Do you want 64-bit? double cone thickness. And then there's also flavor modifiers. You know, you can put syrup to change the taste entirely. And for example, if you want seL4 to run hypervisor extensions for you and guest OSs, well, you want the hypervisor version, which can radically change the flavor of your ice cream. And the final thing is, well, are you happy with a single CPU scoop, or do you want to go multi-core? And so RISC-V has evolved in this manner. And for verification, which runs much slower, providing much stronger guarantees, this is a bit of an issue, because whenever a customer comes and says, hey, I want seL4, turns out very often what they want is not something we have in stock. So that means instead of this nice idea of a mathematical seL4 theorem, what we have is the seL4 theorems, which are really a strategic deployment of multiple assurance levels over a matrix of sorts with of a configuration space which has architectures and features, and this means that the proofs, well, somebody has to keep evolving them and matching up the proofs with the seL4 evolution. And at Proofcraft, we've taken on doing just that. So the first dimension that we should discuss of seL4 proof evolution is the architectures. And by the way, if I inadvertently say that seL4 does not have some feature, I'm a verification person. I mean, it is not verified. So on the architecture level, as I mentioned, when we started this research project, we had ARM, 32-bit, single core, no extra MCS flavoring, but the full verification stack. And we had this thanks to funding from NICTA, the US Army, DARPA, and I believe the Air Force as well. And this was great. And in fact, already after functional correctness, we got some interest. And this was successful. Let's do a real-world demonstrator. Can we do a real-world demonstrator? Well, yes, but there's a little bit of a problem, because if you want to do a real-world demonstrator, you're not going to rewrite all the real-world stuff to go on seL4. So you need some way of having legacy components running on top of seL4. And for that, you need some kind of a shim or guest OS. And that means you need hypervising extensions. So thanks to funding from DARPA, we got to work on exactly that. And our next project was porting the proofs to ARM 32-bit with hypervisor extensions. Now, you might think, textually, these look very similar. There's not that much of a difference. And calling it an architecture is a bit generous. But we had never done, up until this point, ports of our proofs. And they were over 500,000 lines of proof at this point already. And there was commonality, but significant difference in address space layouts, translation, and all sorts of technical details, which made this actually a lot of proof work for verification, because those differences we actually have to reason about. We can't just say, well, here's the difference, and we're done. So that was good. We again achieved a success, and the DARPAs were pleased. But that was the end of significant interest in 32 bits. 64 bits was coming. So what do we do now? Well, it turns out that DARPA was yet again very helpful by offering funding to do a 64-bit port. And we had already done a lot of changes to the verification to enable architecture ports. But the challenge here was, in addition to x86 idiosyncrasies, we were going to 64 bits. And all the proofs in every single place assumed everything was 32-bit. All the sizes changed, everything changed. We had to now parameterize over what size something is, and so on. So this was, again, a significant challenge to build upon our past experience. But again, we pulled this off, and we were quite happy. But the world had moved on. There's not much interest in x86 64-bit for some reason for verification, and no one's really expressed any since. But there's definitely interest in 64-bit, so the work did not go to waste, because a new challenger appeared on the scene. You've already heard Gernot mention the RISC-V open platform. And the RISC-V open platform is absolutely wonderful. People got very excited about it. All we needed was funding. And that we got. Thanks to Hensoldt Cyber, we got to do the functional correctness proofs, and we got to do the binary correctness proofs. It was after that point that Proofcraft was founded and Trustworthy Systems went back to UNSW. And the security proofs were also completed there. And so that means that RISC-V 64-bit now comes closest in terms of parity to our original complete stack of verification of ARM 32-bit. And you would think, well, wonderful, we're done, right? But no, remember the problem with deploying on real-world architecture, on real-world demonstrators is, again, these legacy components. So that means you've got another missing piece. Well, where's the hype? Where's the hypervisor handling? And RISC-V being a rather new platform, hasn't really standardized on the hypervisor extensions. So we can't really do that. And that means the best candidate at the moment for 64-bit with hype is ARM 64-bit. And so thanks to our friends at the NCSC in the UK, Proofcraft has got some money to finally start on a 64-bit platform with hype. And we have funding to do the initial level of the abstract specification and invariants, but we are quite excited at actually getting this done and to parity with the other platforms. So you can see that seL4 has definitely been evolving and keeps evolving when it comes to architectures. But that's not the only axis of evolution. The other challenge is features. Now, Gernot already discussed in the keynote how many different changes he wants to have in seL4 to make it a better operating system. And so verification is at some point going to have to match that progress. And to point out an important difference, there are various levels of features. For example, something like redoing the scheduler to be a highly optimized one was the work of several months. There was another, and we were able to pull that in line. The bound notification endpoints change was quite a significant change to the messaging system of seL4. That took over a year. But we also managed to pull it in line, and people didn't really hear about the verification aspect of this. But the mixed criticality scheduling extension is a different beast entirely. That is taking time and using it as a resource, which means it is extremely powerful, extremely impressive, but it is extremely broad and extremely invasive. And so verification does not have a hope of catching up with this in a year. And to move to MCS, you would then lose all of the formal guarantees. So what situation does that leave us in? Well, it leaves us in the situation that seL4 has two flavors. You have MCS and non-MCS. Non-MCS is where you go if you want all the assurance, and MCS is work in progress, where verification is trying to provide you with the same assurance and eventually reunite these two paths, which brings us to the question of, well, where are we on this? So everything that I have talked about with the architecture evolution, well, that's happening on the non-MCS branch, including the ARM 64-bit work, because we want to provide the assurance quickly and provide it to customers to use. But at the same time, the mixed criticality scheduling verification has not been sleeping. It has been a project that's been going on for quite a long span of time, but it has been on and off as funding was available. So where are we there? Well, we have the abstract specification and the invariants. That was funding from Hensoldt Cyber. Then we have the refinement down to the design spec, and we have that thanks to the Department of Homeland Security. And now Proofcraft comes in, and we have, via the seL4 Foundation, some funding to start on the final phase of refinement down to the formalized C code. So that leaves us in a position where functional correctness is coming close on two platforms. And hopefully, in the future, we can aim for convergence. But before that, there are some significant challenges to keep track of. And that is the main problem that we face as proof engineers is every single time there's a change to the kernel, we have to update all of the proofs for all of the architectures, where we've managed to generalize things that mitigates the proof impact, but nonetheless, this is a constant concern that we have. And while we do this, we come across many proof improvements that would make the proofs better, faster, more generic, easier to maintain in the future. But now we have these two branches. And so any improvements we want to do, we are almost disincentivized from doing because we have to do them again, doubling up the work to do them on MCS. This is one of the reasons that we're doing the ARM 64-bit verification on non-MCS so that we can maximize reuse of proof across architectures. And so the main blazing point which we are going towards in the roadmap is, well, we want convergence. We want to have ARM 64-bit done, and we want to have the mixed criticality scheduling have the same proof coverage as we had previously. And then we can say, all right, now we're done. Mixed criticality scheduling is the version of seL4, and we can give this to the customers and use that one. No more like which flavor and how does it work. So that is the main goal. But there is an additional goal, and that is to figure out in parallel the multi-core situation. Now, we acknowledge that the multiple CPU cores are the future, and seL4 is already adapting to that and has various implementations and working on how to effectively use multiple cores. But for verification, this is a huge problem. Changing the execution model to everything could potentially be in parallel. Well, that is a bit of a challenge. But furthermore, we have 1.5 million or more lines of proof that we don't just want to throw away because we changed execution models. No one's going to wait another 20 years for us to get back to this point. So we need to figure out a way that we can reuse the existing proofs as much as is possible and do it on an execution model that nonetheless says everything could, in principle, happen in parallel. Now, in the past, we have done some investigations on how to do this in theory, and we do have some promising leads there. But to do this in practice is a whole different beast. And so that is going to take a while. But the news is not all bad, because as you will hear in Kent's talk, there is a pragmatic approach to doing multi-core, which is a little bit simplified, well, significantly simplified, as it's a static multi-kernel. But it does allow you to use multiple cores, and it does close up significantly the gap for verification to cover to jump across. And so that will be a starting point towards further multi-core work, hopefully in the future leading to the total convergence of there being one version of seL4. Single core, multi-core, MCS, done. Which leads us to the obvious challenge for reality, and that is, what is the status of the funding? And the status of the funding for the non-MCS version is completing the ARM 64-bit proofs, has still outstanding funding for the 2 remaining refinements to complete functional correctness. And then, of course, we want to do the remainder of the assurance cases, which is the security, very important. You will hear about that in Matt's talk next, and the system initialization and the binary correctness. On the MCS front, as I mentioned, we have funding via the seL4 Foundation to start work on the C refinement, the refinement down to the C semantics. We don't have yet funding to finish that. And then, once that is done, the goal of convergence requires that we bring up the other architectures to parity and also sort out the other proofs, of which the security proofs are a bit more challenging because now you have these scheduling contexts which pop up all around your system, and to say that there's not information flow, for instance, is a little bit tricky to say. But that is the current status, and the message I want to leave you with is you're in good hands. So there's us at Proofcraft, and there's Trustworthy Systems at UNSW, and you can see that the evolution that's been going on with the architectures of the verification has been going, and still is going, and will be going. The features are also being adapted to by verification, and we will continue doing so, and verified mixed grid reality scheduling is on the way, and unification is on the way. But importantly, we are serving our customers now, and our customers are you. So if you want something that is ahead of schedule, or you are particularly interested in a feature or an architecture, or you want to speed up something, please do not hesitate to talk to the seL4 Foundation or to Proofcraft. We are very, very happy to help. Thank you.
Great. Thank you so much, Raf. We have some questions.
So you mentioned the happy but pesky customers. Do you have customers that are asking for things that are not on this nice converging roadmap that are distracting you down rabbit trails?
Well, I mean, the customers are asking for mixed grid reality scheduling.
Yeah.
And
So that's
of
on
course,
the roadmap. So
that's on the roadmap.
Moving you forward.
I mean, you're saying things that are not on the roadmap.
Are there distractions that are,
well,
or is everything kind of fit into this roadmap?
so not everything yet fits into the roadmap, because to put something on the roadmap is to announce it to you, which means we have a plan, right? Like a solid plan, not a we made this up last weekend plan. And so an example of something which people are pushing for that we don't yet have on the roadmap is, every time I've said architectures, I've really been hiding the fact that there are multiple platforms involved. Each architecture has multiple platforms, and they have their little idiosyncrasies. And so depending on which platform the customer chooses, that's not, that might not be a platform we have. And furthermore, it's a bit silly to have to keep porting these, like the verification from platform to platform to platform. If they're similar enough, we would like to just say, look, we support these platforms. Just set it to the platform you want and run the proofs. If they fail, call us, but generally, it should be fine. That is not yet on the roadmap, because we have ideas on how to do this properly, but not something we would announce as like, pay for this now. So.
I may have missed it, but did you say what the plan is for security proofs? So confidentiality, integrity, and so on?
On which branch?
Any. General.
Well, so in general, the confidentiality and integrity proofs are fine. And on pretty much every single architecture, we can pull them off, right? So for AR64, the plan is to have those security proofs. RISC-V already has the proofs. I don't think anyone's really interested in ARM 32-bit hype anymore, but ARM 32-bit non-hype has the proofs. So I think it should be reasonable that on the non-MCS version, everything is fine. For the MCS version, there has been an initial proposal on how to do the access control proofs, so the integrity proofs, and the confidentiality proofs are a little bit more complex, because we could just simplify, we could put massive restrictions on the system you can build and say, yes, seL4 preserves confidentiality. If you restrict your system so severely, it's basically unusable. But we would like to be a little bit more open-minded and say, well, what does actually confidentiality mean on MCS, and what restrictions do you realistically need to impose on the systems engineer? Does that answer your question?
Yes, thank you.
Okay.
Could you pass it just behind you to your left?
Has industry approached you somehow to actually have their platforms verified, so that I sell this board and I'd like that board to be absolutely verified so that it works with seL4, and I know which versions work with my board, so I can advertise this for others?
Well, so the answer to that one is complicated, because it is yes and no. So there has been some interest from platform manufacturers, limited interest, in, hey, could we have seL4 verified on our platform? The difficulty is these are usually very large organizations, and they seem to have a difficulty of figuring out how exactly to fund it. So this is also one of the reasons the seL4 Foundation is an excellent idea, because if you yourself can't fund the whole thing, well, you can join up with other people, pay the foundation, and the foundation can find the appropriate people to hand this out to, and they can do it. So I think that's been the primary obstacle. People are still not yet understanding what verification brings to the table and how important it is and how different it is to just testing and then going, she'll be right, mate. And so I think part of our job is to market this in a more convincing manner. And part of that is the success of seL4. As you've seen, verification follows the kernel. So if the kernel succeeds, people will go, well, but it's verified on that platform, and we want to use it because it's good, so could you verify it on our platform? And now we will make an effort to actually fund it, as opposed to just asking for it because we're interested. So I wish there was more interest, of course, but I think there is some interest, and that is already a very promising sign.
So would Proofcraft take the job of, we're going to use this platform and we'd like to have it fully verified, and if it's not in your immediate path, for example? Let's say a RISC-V that you're not going through, some other flavor, one chocolate flavor on top of it.
Well, so it depends on the complexity, right? The complexity dictates how much it will cost, because that is the amount of time it takes to model it, verify properties. Remember, we don't just model it, we verify actual properties of the system. So if you're able to accept that is going to be the cost, sure, we will take that on board. With one exception, we are not looking at exotic architectures from our perspective like PowerPC. Mm-hmm. I don't think there's any interest from anybody doing verification to do PowerPC, and it's unlikely to change for the foreseeable future.
One question from the online Q&A.
Sure.
Is the kernel initialization code functionally verified?
The kernel initialization code itself, no. So it was verified at one point in the past, but then it received significant changes, and it was not really verified since. But the initialization code for the system is what I was talking about when I said verification. So setting up a system. And I personally would really like to see the kernel initialization be verified. But it is not that bad if you think about it, because if the kernel starts up and the variants hold, we take it from there and everything's fine. And a lot of that is platform setup, things that are below us, setting certain registers and setting things up, and then ultimately, going create a bunch of untyped objects for the user to use. And verification of that is possible. We've done it in the past, but it's not really groundbreaking, and so people aren't very interested in funding it because it doesn't bring that much to the table. It would be lovely for completeness, but not yet.
Great. Thank you so much, Raf and everyone, for your questions. We're out of time for this session, but if you have questions that didn't get answered, direct them to me. My name is Nick Spinell. You can find the spelling of my name in the session chair. Call with the program, and I'll try to get them answered for you. But yeah, I think we're ready for the next session. Let's give a round of applause.